Hello, this video is inspired by a problem that David is currently having. David is a young executive working within a material testing laboratory, and they've been delivered with batches of unidirectional composites, and they're required to test them. But when he started investigating those composites, he realized that some batches of this composite had voids all over them. And so they decided, okay, we might as well throw these voids, these voided composites away. But then because he has had some experience, with computational modeling, decided to do a numerical modeling of this problem to see actually if this void has a detrimental effect on the composites. So this is what we're going to do. We're trying to use this video to show how you can model composites. At the end, the kind of result you'll be expecting will be something that looks like this. Basically, it's a comparison between the unvoided composite to the left, the right, and the unvoided composite on the right. And you see the kind of behavior that they are showing. Also, when we look at the mechanical behavior, you notice that, okay, the voided composite and the non-voided composite had different results. So this is the object of what we're going to do in this video. So let's sit back and relax as we try and help David solve this problem. So as we start, we are going to be moving from a voided composite to try and generate this kind of result. But let's look at what the analysis framework would be for David's problem. So clearly, David has to follow a microscale approach in investigating these problems. So we're looking at the metrics. The metrics has to create the voids, and those voids will have to be added together with the voids extracted from the metrics to give you a voided matrix. So this will be the way to start. So he creates first the voided matrix, then he takes the voided matrix, add the fibers in their constituents, the way they are formed, and then he will generate the voided composites. So this is how the analysis framework would be for creating the virtual domain for this problem. With that, what are the typical numbers? So he needs to think about the dimensions that he wants to use for this problem. So the length, the width, and the height will be 120 microns. And these are the properties of the material that would be investigated here, which is a glass fiber reinforced composite with a Young's modulus of that. The matrix will be polypropylene. Typical things that you need to think about here would be the volume fraction of the fiber, which is around 34-35%. The fiber is 30 micron in diameter, and the morphology of the voice, which means the shape of the voice, will be, again, each voice would have a spherical shape of 30 microns, and typically a volume fraction of 8%. So this he could do by microscopy to investigate what percentage of the volume actually consists of these voids, and this is the parameters that for this instance that David is trying to investigate. Now, okay, we've got a Monte Carlo generator for 3D, which is a software that I've developed for creating these voids randomly, because it has to appear randomly within the matrix. So with that, you get certain coordinate positions indicating the positions of the centers of the spherical voids. And with that information, you now go into ABAQUS to create the voided matrix. So this is the analysis flow that you want to work with. But then that's just the matrix that is voided. Then what would he need to do about also the fibers? So again, another software that I've created, Monte Carlo Gen, the 2D version, use that to create this random positioning of the fiber. And then these are the typical dimensions that we're going to use. The only difference that we added a third axis here, which is the z-axis, indicating the positions in space of this fiber in a three-dimensional sense. So that's the initial thinking that David has to go through if he's going to go into modeling this kind of problem. Just to give a flavor of the kind of results that he would be looking to get. So two case studies, the first one being a transverse tensile deformation, and the second one being, again, the same kind of deformation, however, for the non-voided composites. So that's the setup. So let's jump into ABAQUS as we begin to do this modeling. Okay, so here we are in ABAQUS, and of course, you can start modeling this, from first principles and then build on to the end. If you look on the card, I've provided a link for you to look at how this can actually be done, for UD composites, from first principles without any need for a script. But however, in this case, we are going to use a script to investigate this. So this script will be available for you to download in the link. So what we're going to do now is to get hold of the script. So we do file, run script. So you navigate to the location where the script is located. Okay, so here I am. The script that I'm looking for is first, we'll do the non-voided case. So we'll select that. And basically it creates the problem that we're trying to do. So if you just study it a little bit more, so we've got the voided matrix, and then we've got the fibers in their positions created automatically for us. So we need to clearly extrude cut. So we select that, and and then you follow this, get that bit out, just to cut off the extra fibers, and then we get a proper domain that represents the structure that we're dealing with. So this is fine, this is okay, this is what we'd expect. So clearly there is a bit of intersection between the fiber and the voids, but that's not a problem, because the composites, the fiber will take over in those environments. Okay, so the first thing we need to do here is to make sure that we have all the fibers correct. So I'll select the matrix only and remove that. So this should also be a part of the matrix. So I remove that, leaving only the fiber in place. So double click on the fiber, pick everything that makes up the fiber here, and click done. So we've got a component that represents a fiber. And then if we invert this system, this selection, so that leaves us with the matrix. So we double click on the matrix and pick everything that represents the matrix. Okay, then you return everything, and then we can just check that we're happy. So yes, so we're happy with all the properties, everything looks all right. So quickly, let's mesh the domain. So again, you can use whatever default. I would like to use a tetrahedron to mesh it. Okay, so the mesh is generated, and this is correct in the way it should be. So what we're going to do is we're going to query these corner nodes. So query that corner node, and it's 120.0.120. So let's create a reference point to that. So while we are in the assembly module, so tools reference point 130.0.120. So that means that's a reference point that we're going to use. So still in the assembly module, so we create a set of that reference or reference point set, select it on this model. Okay, now, so we're going to then use that to apply our boundary conditions and also to apply our loading. So let's just go ahead and create all the boundary nodal sets. So the first thing we're going to call here is X front. So X front, I'm going to do it based on the node. So, and I'm going to change this to biangle. Okay, so you just hover around until you have all the front sets selected. So we're going to repeat that for all cases. Okay, so we've created all the sets. So let's just check. So back, front, Y base, Y top, Z base, Z front, and Z back. So that's all done. Then the next thing we need to do while we're still thinking about this is create the loading step. So this is our loading step. Okay, static general is fine for a start. And then we'll probably need to create some history output. So this will be my reference point history output. So we're going to use this to extract the reaction forces. So on the set reference point, the history output point would be reaction force in one direction and displacement in one. So we're just going to use those two. Again, you could pick them up by going to this case, which is RF1, and then displacement. If you go to this case U1, so U1 being the X direction, which is the direction that we're going to. So we're only tracking those particular values. So then the other thing we need to probably do is to do a constraint equation. So we'll do a constraint equation. So we'll do a constraint equation based on equation, and it will be 1 on this axis, 1, and this will be X front, degree of freedom 1, minus 1, reference point, degree of freedom 1. So that makes a connection between this and that. Then we can also apply displacement. So our extensile load extension would be applied on that reference point. and it will have a value so of 10. Let's do up to 10%, which is 12 microns, because the length of this is 120 microns, so that's 10%. Then the other bit is to just apply the boundary condition. So let's do that. So here for the right boundary condition will be X back roller, initial conditions, X back highlighted, that's what we want in the one direction. Okay, now we'll do the same for the other direction. Z back roller. Okay, so we apply the boundary conditions with the back fixed in the one direction, the Z back fixed in the three direction, and the Y base fixed in the Y direction. So we've got our loading history implemented. So let's just then set up the model to run. So the polypropylene here needs to also include plasticity to allow it to show plastic deformation. So for 40 e to the power 6 and 0 with the plastic value for the polypropylene that we have in our model. So this allows for plasticity to engage. So now we submit the model to run, and the model will start running. So let's then go to the next case. So I'll create a model 1. We need this model to be open for the script to run. So we're going to run the next script. So we'll run the next script, navigate to that environment. So the non-voided case. So it comes in as here. So all the properties, again, we'll check to make sure that the assignments are correct. So first thing we're going to do is to hide the metrics. So if I select this and say, okay, I want only the metrics to be hidden, leaving behind the fiber, okay? Or maybe before we do that, so first thing we're going to do here is to extrude cut on this model. So still there. So in the path module, so we select that region. Okay. So now we get that corner, those two corners. Okay, this is fine. And then we can cut out the whole thing as well. Okay, so we've trimmed up all the fibers. Leaving behind the actual shape we want. So we can then check out the sectioning again to make sure it's right. So if I select that, I'll deselect remove that bit. Okay, so this is a fiber. So we select this fiber, making sure it's looking right. Okay, then invert that, leave behind the matrix, then go back and select the matrix. Okay, so we restore everything. So everything is the same as in the previous case. So we're just going to apply all the information that we had before, and then we get this model ready to run again. Okay, so we've set up the second case. We've got all the boundary conditions in place as we'd expect them. So the back fixed with a load in front, with a constraint equation which links this to that, just like we did previously. And the history variables, so the history we're tracking is the reaction force and the displacement of the reference point set. So we've got everything ready, and we've also created and submitted the model, so it's running now. So we're going to come back and have a look at both of them when they finish running. Okay, so both models have finished running. So here we have the voided case relation that shows you what's happening here. So if we rotate it around, you could see where the voids are. They are clearly not contributing to the load bearing of the system. So this is a challenge that David will have in trying to use this to generate elastic properties for this composite, because clearly these voids are not contributing in load bearing for this composite, and so it becomes a problem, especially if you think about this edge, where you've got this fiber protruding out. So that's a challenge for David if he's trying to investigate this problem and trying to use this to make some meaningful results. So if we also look at the voided case, which is the ideal case that you want. So the plastic strain looks all nice. Every part of the model is playing a role in contributing in load bearing, which is what composites are. So this is the ideal behavior. You get a shear band forming on those two sides across in this model, a clear picture. So if we put the two together, you end up with a slightly different behavior. Clearly here you have clear shear bands forming there, but they're not very evident in this case because of the effect that you see there of the fiber being of the matrix being voided in those regions. Yeah, so this is a challenge that you get in all this in this kind of example. So if we then try and do some kind of animation of this, so you could see what David is dealing with if he's trying to model this problem, because then you're having this different behavior for the material. So that's what you can see numerically by just doing simulation. But what would really be interesting here is for us to do um, a quantitative analysis to see if we can generate some stress strain data from this. So how do we go about doing that? So clearly you go to create XY data because we have a history output that we've created. Now within this history output, we're only tracking some parameters here. The reaction point, RF1, so you could also include the other case and U1. So in this simulation, I included the other cases, but what we really want here is the reaction force one and the displacement one, then you plot that. So that gives you a measure of the force and the displacement. So we're going to take that data into Excel from current plot. So this will load Excel and load the specific data that we have in mind. So what we're going to do here is we're going to copy that data. So I've already created a script which we're going to use here. So this is the data. So if we put this data in here, so what you've copied for the voided case, so we'll do the same for the unvoided case of those. So again, we look at the data that comes with it, which is the reaction force in the one direction and the displacement in the one direction. So we plot that. So that generates some data for us. So we can then look at the analysis that, so get that plot. So it will then again import the data into Excel for us. So we copy that data. So I'll paste it in this environment for the non-voided case. So this is a template. I'll provide this Excel sheet in the link of this video so that you can also use it if you really want to use it. But there's nothing really exceptional about this. So what we are trying to do basically is that the reaction force in the x direction or one direction and the displacement in that direction. So if we use that, so the force will be exactly that same force, the strain. What would the strain be? The strain would be basically the displacement divided by the original length in the x direction, which is the length of the material. So I've already indicated here. So if you're using this script, you then, if your RVE size is changed, you need to change those values. So 120 is our length. Then I apply it across the domain, and the stress will be equal to the force divided by the cross-sectional area, which will be the width times height, and that already has been specified here. So we can end up having this kind of plot. So what we need is the Young's modulus of this material. So it's the slope of the linear elastic region, which is basically these first 2 points. Okay, clearly this simulation jumped from 0 to this yield point rapidly, which is not ideal. So maybe you need to reduce the time step to allow for more gradual build up. But this is how the simulation came up, which is fine. It's not a problem. So we get that as our Young's modulus. And what is the strength? The strength is basically the absolute maximum value, like the ultimate tensile strength of this composite. So you end up getting that value around there. Okay, so we get that for the non-voided. For the voided, the same thing will apply. So we get a different plot. This one, there was a gradual build-up due to the effect of void. So you have a gradual build-up as dissipation of energy within the matrix begins to happen. So you end up with that. Then the final thing I did was to put them all together, and you could see the difference. So we've got a Young's modulus for the voided case slightly higher than the Young's modulus of the non-voided case. And that's mainly because of this sudden rise from 0 to that. So if you increase the mesh size, maybe do a bit of mesh dependency study, I don't expect that there will be much difference between the moduli in both cases. Okay, they're approximately both equal to 2 gigapascal, which is all right. Because in the elastic region, the effect of the void doesn't really play a significant role. I wouldn't think. However, once you start getting into failure, that void becomes significantly important. So you can see now that you've got the voided case here and the unvoided case on the top. So the more you have voids, the more the strength of the material is degrading. So coming back to the problem that David had at the beginning, he cannot really use those voided composites, even at 8% void percentage, because there is a massive reduction in the strength of the material. There is also uncertainties around what happens in the elastic region. So the original idea of throwing away those samples and just getting a new batch would probably be the right way to go. And hopefully at this end, we've been able to help David come to the root of what he needs to do about those voided batch of composite materials. If this is the kind of content that you like, please do subscribe to this channel so that when I make content like this, you'll be the first to see it. If also there are ideas of videos you would like me to make, please do tell me about them. And please click the like button so that the YouTube algorithm would continue to push out these videos to people like you who are keen to benefit from insights about computational modeling. Take care, and I'll see you in the next video. Bye bye.